folks, Miss Stryker here. I wanted to make a video to accomplish two goals. One, I wanted to talk to you about the AP exam, the 2020 AP exam that most of you are taking in just 2 weeks, and tell you what I know about the kinds of questions that you're going to need to answer. And secondly, I'm going to use my template, which you can see here in the background, to do a little review of rotation. And then this week, you're going to be working on some rotation problems as well as some paragraphs. All right. And so I made myself some little cheater note cards for you. So normally the AP exam is an hour and a half of multiple choice questions and an hour and a half of free response questions. And that is not true this year. It is only free response and it is only 2 questions. A normal year would have 5 free response questions, and the College Board uses the same kinds of questions every year. So they have an experimental design question. They have a paragraph length response question. They have a qualitative quantitative translation question. They have a short question versus a long question. So they have shared with teachers and you all what types of questions you're going to have this year. And I thought that I would tell you very explicitly what those are going to be. And so you're going to have 1 short question and 1 long question. And so here's my little card. 2 questions, 1 short and 1 long. They usually specify the long question should take you 25 minutes and the short question should take you 15 minutes. And in a normal year, the long question is worth 12 points and the short question is worth 7 points. I have no idea whether they're going to have them worth different point values. I don't know what the point values will be this year. But so 2 questions, a long and a short. They have told us that there is going to be a quantitative, qualitative translation question, as well as a paragraph length response. And so that means in one of the questions, whether it be the long one or the short one, part of one of those questions is going to involve you writing a paragraph. And probably the longer question will be the qualitative translation question. All right. That probably doesn't mean anything to you, and that's just fine. I never use that terminology, but I will tell you what that means. So qualitative quantitative translation simply means describing with words and then supporting your description with math. So quantitative is a description, qualitative is math. All right. And so the way to handle that kind of question is to start, when you're doing your math, make sure that you start using something from the formula sheet. Don't start with a formula that's already partly derived from your textbook or from your notebook. You've got to start with the formula sheet. Start there and then derive from there. All right. Also, think about big ideas. Big ideas. It's very important for you to be thinking as you read a problem, what are the big ideas that govern the solution of this problem? So it might be that you use a free body diagram. And often when you use a free body diagram, you think about Newton's laws, F equals ma. It might be a conservation of energy problem where you know there's no friction. And so you can say the initial potential plus kinetic energy of the system is going to be equal to the final potential and kinetic energy of the system. Maybe there's some work being done. So potential energy plus kinetic energy plus work that might be done to remove some energy from the system is going to equal the final potential and kinetic energy. So maybe it's energy, maybe it's an F equals ma involving a free body diagram. Maybe it's a momentum problem where there's a collision and you have to say initial momentum is equal to the final momentum. What else? Maybe it's a simple harmonic motion question. It could be that. Or maybe it's rotation, rolling without slipping. We're going to do some of those examples today. So think about the kind of problem, the big idea, and then go forward with your solution. And then you can probably expect to see an experimental procedure. Not sure about that. They didn't say that, but it wouldn't surprise me at all if they did that. All right. Put some sort of write a procedure for this or that. What about the paragraph length response? So if you're prompted with in a well-formed paragraph, that means they're looking for a paragraph. That's when you should write a paragraph. So here is what you should do for a paragraph. 4 to 5 sentences, not 2 sentences, not 3 sentences. Don't write 10 sentences. Think 4 to 5 sentences for a paragraph. That means you have to be concise. So you can't sort of ramble on about all kinds of different things. Think about the main idea. What is it you want to communicate? And then write about that. Try to be concise. Think about what those big ideas are. We just mentioned them. Free body diagram indicates Newton's laws, energy conservation, momentum conservation, simple harmonic motion, or it could be a rotation problem. What are the big ideas? Reason why you're using the method that you're using. Oops, there I am. And then make sure you support the big ideas with those following sentences in your paragraph. All right. So that's what you should think about for your paragraph. We're going to do some practice this week with paragraphs. If you're not prompted for a paragraph, if you're just said to explain the following, that means write a sentence. You don't need to write a paragraph if it just asks you to explain something. All right. So look for the word paragraph. And last but not least, on May 4th, you are going to get a login opportunity to practice logging into the College Board and do some sort of practice test just to make sure everything's working. That is 10 days before your exam. And so look for that May 4th. Look for your, I think it's called an e-ticket that you're going to get in your email. You're going to need that e-ticket to log in. So on May 4th, you'll be able to practice that. All right. So that's what I know about the test, but please email me if you have other questions. I'm going to flip my my tablet now down on the table so that I can go over a little bit of rotation review. And this week, that's what you'll be working on. All right. So you're going to hear a little noise here for a few minutes, and then we'll go forward with this rotation review. All right. So as we did in class, we're going to look at the rotation unit, which is sometimes a little troublesome for students, but really, if you think about it the right way, it is exactly like solving any other problem. If you know where to start and you know how to go about the process, you can usually arrive at a pretty good answer. And so I'm going to start with what we know about translational motion, and then derive or write down the analogous rotational formulas from there. All right. So for translation, what are our formulas for kinematics? V final is equal to V initial plus AT. What else do we have? Displacement is equal to V initial T plus 1/2 AT squared. And then our time independent equation, V final squared is equal to V initial squared plus 2 times the acceleration times the displacement. Kinematics formulas. Remember that these formulas are derived with a constant acceleration. So you can't use these formulas if acceleration is not constant. For simple harmonic motion, you do not use these formulas. All right, you probably have to use conservation of energy for simple harmonic motion. Regardless, there are analogous equations for rotation. So final angular speed is equal to initial angular speed plus alpha t. Alpha measures in radians per second squared. Omega measures in radians per second. So angular speed versus angular acceleration. We have an analogous displacement equation. So angular displacement plus 1/2 alpha t squared. And then we have a time independent equation as well. So final angular speed squared is equal to initial angular speed squared plus 2 alpha times the angular displacement theta. All right, translation and rotation. Moving on, what is the big formula in dynamics that we use to talk about something that's translating? So it's F net equals mass times acceleration. The analogy for rotation is that the torque net equals not mass, but moment of inertia times alpha. And remember that torque is defined as a force crossed with a radial vector. Actually, I need to rewrite that because the order matters. It's the radial vector crossed with a force. And what that really means is it's the radius vector, the vector between, what is the radius vector? It is the radial vector from the axis of rotation to where the force is applied. That's how long it is. So it goes from the axis of rotation to where the force is applied. Radius vector multiplied by the force vector multiplied by the sine of the angle in between those two. So please do have a look back at torque. And then if they're at 90 degrees, the sine of 90 degrees is just going to be 1. And so it becomes R times F. The simple form is R times F. Look back at torque. All right. So we have torque and we have F net. Those are our dynamics equations. The last really important formula that I think you're going to probably need to use is the kinetic energy formula. Kinetic energy for translation, 1/2 mv squared. And for rotation, the rotational kinetic energy is 1/2 I omega squared. All right. And let me also write down the momentum. So linear momentum is equal to mass times velocity. Angular momentum, another conserved quantity, is I times omega. I times omega is angular momentum. For a point mass that's moving in a circle, and this might be a satellite or a moon or a planet, or it could be a little rubber stopper that you're swinging around your head. If this has a mass m and a radius that's constant r, and it's moving in a circle, the angular momentum of that is equal to its moment of inertia, and that happens to be m(r) squared times omega, which is v over r. And so that simplifies to mvr. All right. And so for planets moving around the sun, if the radial distance goes up, the velocity goes down. mvr is the angular momentum for a point mass moving in a circle. All right. So those are important quantities for translation and rotation. How does translation relate to rotation? Well, we start thinking about this in pre-calculus when we learn about the circle and slicing it up in sections. And so this distance along the edge is called the arc length. And there's my radius and there's my angle. And so the arc length is equal to the radius times the angle, as long as the angle is measured in radians. Arc length S measures in meters. Now, if I divide each side by time, I get velocity is equal to R times omega. And if I divide by time again, I get acceleration. Tangential acceleration is R times alpha. So that's how translation relates to rotation. And that'll be something for you to keep in mind. All right. What about moment of inertia? So I, this weird thing I. So moment of inertia is really resistance to changes in motion. All inertia describes resistance to changes in motion. Things that rotate, instead of mass, they have what's called a moment of inertia. And that describes not only the resistance to changes in motion, but where the mass is in relation to the axis of rotation. So if the mass of a system is far away from the axis of rotation, there's a big moment of inertia. On the other hand, if the mass of a rotating system is really close to the axis of rotation, then it's a small moment of inertia. All right. And so let me write down the moment of inertia for different objects or systems. All right. So what about, we just said a mass, it's moving in a circle with a radius r. So that has a moment of inertia of mr squared. You should know that. You should memorize it. It should be easy. What about a disc or a cylinder, like a can of tuna fish or a can of pineapple? All right. Let's say it's got a radius of r and it has a mass. Well, in that case, more of the mass is close to the center. So that has a moment of inertia of 1/2 mr squared. And here I should have used capital R, r squared. What about a softball, a solid sphere? Solid sphere. So the moment of inertia there, well, now there's even more of the mass close to the center, close to the axis of rotation. If it's spinning around the center, 1/2, whoops, not 1/2, dirt. There we go. It is 2/5 mr squared. All right. And last but not least, a hoop. If you have a hoop or a ring where all the mass is at the edge, the moment of inertia is again mr squared. So it's the same moment of inertia as a point mass moving in a circle. There's a hoop, here's a disc, and here's a sphere. So some good moment of inertia shapes to remember. All right. Okay, before we do a few examples, let me talk to you about rolling without slipping. So let's imagine we have a bike wheel, a bicycle wheel, and it's rolling along, happy as could be. Okay, and it's not sliding or slipping. There's no ice on the road. It's just rolling along. And a few minutes later or a few seconds later, it's going to have moved down here. All right. It's just going to continue to roll. So this thing is not only rolling, but it's also translating. It's moving to the right as it moves. And it's not slipping. If it's rolling without slipping, there has to be a force of friction between the surface of the road and the tire in order to keep it sort of sticking to the road as it rolls. So it's not going to slide, it's just going to roll. So there is always a force of friction if there's rolling without slipping. Okay? And if you've got an object that is not only rotating but also translating, you have to use both rotational motion and translational motion in order to solve. You need to use both of these things in order to solve those problems for the most part. All right, so let's do a few examples. Here's an example. So what I have here is a disc. This is a disc with a radius r and a mass m. It's a disc. It's attached, well, it's got a cord, a disc with a cord wrapped around the outside. And let's assume that the cord is massless. And I'm just going to let this thing drop from rest. Maybe the cord is attached to the ceiling at one end and it's going to unwind and drop. All right. And I would like to know, what is the acceleration of that mass, of that disc? Okay. Since it's a disc, I know its moment of inertia formula is going to be 1/2 mr squared. So that comes from the fact that it's a disc. And I'm going to have to be able to put together rotation and translation in order to solve this. All right. So let's first think about a free body diagram. So here's my disc. I've got what? Acting on the center of mass, I should say, is the force of gravity, which I know is mg. And acting at the edge is this tension. The cord offers some tension that's going to impede the acceleration a little bit. So if I get a value for acceleration bigger than g, I ought to be pretty surprised, right? It's going to be less than g. That tension is going to impede its acceleration. Those are the only two forces acting. And only one of those forces causes a torque, right? So there's the radial vector from the axis of rotation out to where the force is applied, happens to be at 90 degrees. So that should be a pretty easy torque calculation. Okay, so here we go. Translation and rotation separately. So for translation, we always start with F net equals MA. Now I know this thing is going to be unwinding clockwise the way I've drawn it. So I'm going to use clockwise as positive, my positive direction. And I also know that it's going to be translating downward. So I'm going to call down positive. Down positive. So the downward force is the force of gravity, mg. The upward force is tension. Those are the only two forces, and I need to subtract them because they're pointing in opposite directions. mg is going in my positive direction, equals ma. Okay, so I'm pretty much done. If I want to, I can rewrite this by moving tension over here and bringing MA over here. I'm going to eventually do that, but right now I really don't need to do that. We'll do that in a second. What about rotation? So the net torque, I have to add the torques together, equals I alpha. Well, there's only one torque. It's caused by tension, right? Don't confuse tension, which looks like this, with torque, which looks like this. If I'm writing down a torque, I need to multiply a force times a radius. So the force happens to be tension, and the radius happens to be R, okay? Equals I 1/2 m R squared times alpha, which is A divided by R, okay? Now, as we saw in class, all kinds of things cancel. R cancels here, and then R cancels here. So now I have an equation for tension. Oops, let me use purple. Tension is equal to 1/2 MA. And if I rewrite this translation formula, I can rewrite it as mg minus ma is equal to tension, okay? So now I've got a formula for tension here and a formula for tension here, and they must be the same. It's the same tension acting on that disc that's unwinding, or the disc that's rolling without slipping, unwinding along because of the pull of the cord. All right, so put these together. Mg minus Ma equals 1/2 Ma. Bring the A's to the same side. So Mg is going to equal Ma plus 1/2 Ma, which is 3/2 Ma. Mg is equal to 3/2 Ma. Lo and behold, you can get rid of M's. And if you divide each side by 3/2, last but not least, you get the acceleration as 2/3 g, and that makes sense. It certainly is less than g, okay? So that is what I would hope to see, or what I would expect to see for that kind of a problem, using both rotation and translation. A similar problem is a yo-yo. You can look this up online. It's done online. Please do find it and take a look at it. It's a little bit different, but very similar to the problem we just did. It's a little more complicated because a yo-yo, if I were to turn this around and look at it from another angle, it's two discs that are sandwiched together by a dowel in the middle, right? There's this little dowel in the middle and two discs on the outside. So actually 3 discs are stuck together, okay? So if my large disc has a mass of capital M and a radius of big R, and my small dowel in the middle disc is a mass little m and a radius little r, my moment of inertia for this shape is going to be I of one disc plus I of another disc plus I of the small disc. So 1/2 big M R squared plus another 1/2 big M R squared plus 1/2 little m R squared. So it's going to be M R squared, adding these together, plus 1/2 little m R squared. All right. A moment of inertia is more complicated, no doubt about it. And so that will come into play in the rotation part here. And when you're working with torque for the yo-yo, the torque is applied to the small disc, and so you need to use T times little r is going to be equal to the torque. All right, so it's a little more complicated, but certainly doable. So please do look this up online and make sure that you can see how to solve a yo-yo problem. I know you all can do it. All right, so on to the last problem. Excuse me. The last problem I have for you is a pretty common problem. What if we had a ball that was rolling down a ramp and we wanted to know the acceleration? What's the acceleration of this ball rolling down a ramp? So let's say it's a sphere, like a softball. So it's going to have 2/5 mr squared. Here's the r, has a mass of m. It's going to start from rest, initial velocity equals 0. It's going to roll down the ramp that's inclined at an angle theta. Maybe it has a particular height h. You know, you could apply conservation of energy to this and find its final velocity. We did that in class. But I want to find its acceleration on the ramp. All right, and in order to do that, I need to apply both translation and rotation formulas. Need to consider both, and again, put them together. So that's my strategy. So let's first draw a free body diagram. All right, so I'm going to try to copy that incline. So there's the incline, and I'm going to do a free body diagram. So there's my ball. Well, I didn't do a very good job with that ball. Actually, let me get rid of the middle. There we go. There's my ball. So for a free body diagram, if you're doing a free body diagram due to rotation, you need to do that a little bit differently. Almost always they ask you for a rotation problem to draw the forces from their point of application. And so what about the force of gravity? Well, that acts on the object's center of mass. What about the normal force? Well, the normal force is coming from the surface, normal to the surface, and actually pushing up in this direction. And there's a force of friction on the ball that's going to cause it to rotate. So static friction on the edge of the ball. All right. So we need to show those forces, and we need to show them from the point of application. And so I wonder if I can move this line. I can't move that line. I know there's a way to do that, but I'm not going to do that right now. Sorry about that sound. Let me go back and put my surface here. Doesn't quite match, but I think you'll get the idea. So my force of gravity starts at the center of mass and points straight down, mg. My normal force, I drew that in a light blue color. Normal force, well, that comes from the surface and it points normal or perpendicular to the surface. So there's the normal force. And last but not least, the force of friction is applied sort of tangent to the edge. And if that object weren't able to roll, it would actually hold it in place. So it's there at the edge. That's my free body diagram. All right. So here we go with translation and rotation. Translation. F net equals ma. Well, what are the net forces? I know that this ball is moving in that direction, so let's call that the positive x direction. And I know it's also going to rotate around like this, so let's call clockwise the positive direction. So what force is causing it to go down the ramp in the positive direction? Well, it's one component of gravity, right? It's that little component of gravity. And so what does that look like? mg sine of theta is the force pointing down the ramp minus the force of friction, which I neglected to label up in my drawing. And that's going to equal mass times acceleration. Again, I can rewrite this if I want to. mg sine of theta minus ma equals force of friction, only because I know that I'm going to get another formula for force of friction from the rotation side, and then I'll be able to put them together. All right, so that's translation. Rotation. Torque net equals I alpha. Torques are force times radial distance times the sine of the angle in between. In my case here, the only force that causes a torque is the one acting at the edge, at the acting tangent to that ball. So it sort of touches the edge of the ball. The other two forces go through the center of mass, and so the radial distance would be 0. They do not apply any torque. So my torque comes from the force of friction. All right, force of friction times the radius is equal to 2/5 mr squared times alpha, which is really A over R. And again, we love it when things cancel. This R cancels, this R cancels. And in the end, I get force of friction is equal to 2/5 ma. So now I've got friction in two places. I've got two equations involving my two unknowns, A and force of friction. I can solve for either one. So let's just solve for acceleration because that's what I wanted. mg sine theta minus ma equals, now I'm going to use this force of friction, 2/5 ma. Get the a's to one side. mg sine theta equals ma plus 2/5 ma. That's really 5/5 plus 2/5, which is 7/5 ma. I should be writing capital M's instead of small m's. All right, big M G sine theta is equal to 7/5 big M A. Regardless, the M's cancel, as is almost always the case. A is equal to 5/7 G sine theta. Okay, so I am going to ask you to copy these notes into your notebook, take a picture of it, and submit it to me so that I know you're engaged with this review process. And then you'll have some work to do this week with rotation review, as well as some practice with paragraph length response questions. All right. I hope you all have a great night, and I will talk to you soon. Bye-bye.